select stages. So their main aim is to take in, if I were to draw, to take in a sequence of renamed instructions get the renaming done, and subsequently, I'm sorry, they take in a sequence of renamed instructions and get them added to the instruction window. That's what I meant to say. So some of these instructions would have both of their source operands ready, some won't. So for the ones that are not ready, well, we wait for the source operands to be ready. And for the ones that are ready, we send them to the execution units, right? So, so of course, if they are ready, we need to read the register file first, and then we read the register file, and then we send them to the execution units. So let us look at the first stage, which is the dispatch stage, and then we will introduce the other stages first. First a high level view, and then we shall get into the details. So until the rename stage, instructions proceed in order, in program order. After that, they are entered into the instruction window. This also happens in program order because the input of renaming is in program order, the output is also in program order, and the instructions are entered into the instruction window from the rename stage. So this process is known as dispatch. So different books or different sources can use different terminology, and some might confuse dispatch with a related term called issue. But we will use this convention that transferring instructions from the the renaming stage to the instruction window is the dispatch stage. So the instruction window is essentially a set of instructions, and it is typically organized as a circular queues. Almost all queues in hardware are organized as circular queues. The reason being that a queue is essentially a software concept that is meant to be implemented using a linked list, but this is rather hard to do in hardware, because in hardware we cannot implement such a complex thing as a linked list. So what we have is we have a single array of entries, and we have, as discussed before, we have multiple pointers, two in this case, a head and a tail, and they wrap around. So this is a very standard design that is used in a large number of hardware structures. The instruction window most of the time uses something similar. So what is the status of an instruction in the window? What are all the fields, right? So it has a lot of information associated with it. So let us go over them one after the other. So the first field is that is the entry valid or not. So almost all queue-based structures would have such a single bit entry, right? So this is a single bit. It's a 1-bit entry to say if the entry over here is valid or not. The next is the opcode. So the opcode is the operation code of whether we are dealing with the add, subtract, multiply, divide instruction. Then we have information for each source operand. So we in our RISC instruction set, we have a maximum of 2 source operands. So if it is an immediate, we store the immediate value over here, because this comes along with the instruction, and it needs to be stored somewhere, so it is stored over here. If otherwise, if it's not an immediate, then what we do is we store what is called the source tag, and the source tag is nothing but the physical register ID. So it is just the idea of the physical register if we are talking of a register operand here, and this is the ready bit. So the available bit that we read in the rename table, the ready bit is definitely related to it. Well, how? If the operand is an immediate, well then the ready bit is 1. Otherwise, the ready bit is the same as the available bit of the rename table. So what did that bit indicate? Well, that bit indicated if the instruction, if the first source operand in this instruction, if it is ready or not. If it is ready, then we directly read it from the register file, or we read it from the forwarding network. So forwarding is primarily an in-order pipeline concept. So we have something very similar in out-of-order pipelines, because whenever we have multi-cycle functional units and we do need forwarding, right? So there is no escaping from forwarding, but it has a different name. So we will henceforth use the different name, even though they mean exactly the same thing, in out-of-order pipelines. So in out-of-order pipelines, instead of using the term forwarding, we'll use the term bypassing. So bypassing, forwarding, same thing. Forwarding in order pipelines, bypassing out-of-order pipelines. And the ready bit basically indicates if either we have the data with us, which means it's an immediate. So we of course have another bit to indicate if it's a immediate operand or a register operand, that I'm not showing. And it stores the source tag. Source tag is nothing but the physical register ID. Similarly, we have exactly a same copy of this information for the second source operand, if there is one. And also we have the destination tag, where the destination tag is that if this instruction has a registered destination. A lot of instructions don't. For example, the store instruction does not have a registered destination. But if there is one, what is the physical register ID? Corresponding to this instruction, right? Corresponding to this destination. So that is the most important aspect over here, that we basically store and deal in terms of these tags. All right. So we will see that this will become important at a later stage. So at any point in the instruction window, what will happen is that we'll have a set of green instructions and a set of red instructions. The green instructions will be those instructions for whom all the operands are ready, right? Whose operands means all the operands, right? Not one or two, but all the operands are ready. So they will be the green instructions. And we'll have a set of red instructions, which are just, so red means kind of like a traffic light, stop there. So these are instructions which are waiting for an operand to be ready, right? So either one operand or both operands are not ready, so they are waiting. So let us look at this part of the pipeline. So the earlier part, what did we have? We of course had fetch. So fetch had a host of things like branch predictors and so on. Then we had decode. Then we had rename. And then we essentially, this process is known as dispatch, where we write it to the instruction window. And at any point of time, we will have a set of green or ready instructions and a set of red instructions that are essentially waiting, right? So these instructions are waiting for one or both of their operands to be ready. So out of these green instructions, a few of them, well, all of them we can execute, but let's say that we have two adders and all four of them are add instructions. We can only execute two out of these four. So let's say they are these two. So these two instructions essentially get selected. So we have a select unit. So it selects these two instructions. They read their value either from the register file, or of course what I'm not showing here is that we have a full bypass network here, right? We have a full bypass network here, okay, from the different values that are being written. and we have a full bypass network here at different stages, right, and even from within. So we have a host of it's similar to forwarding. We have a large number of multiplexers, so this is the bypass network, so it's not being shown for the sake of simplicity. So it doesn't matter where they get the value from, they get it either from the register file or from the execution units, doesn't matter. So I'll just show the animation once again. They get selected, right? So at this point, structural hazards can happen. It's an out of order pipeline, so definitely structural hazards can happen. So as I said, we could have only 2 adders out of these 4 execution units, and all the 4 green instructions shown over here may be add instructions. So we just choose 2 of them. Well, how do we choose? We will discuss that in detail when we discuss the select unit. And how do we know who's ready and how is this information propagated? Even that will also be discussed, but this is just the high level view. So in the high level view, we choose 2 instructions, select them, read their source operand values, and execute. So now that we have seen the overall picture, let us now start looking at each of these individual stages in great detail. So let us kind of elaborately look at each of these specific individual stages. So some of the key questions that we need to answer over here is that consider an instruction in the instruction window that does not have one of its operands ready. So how does it know that one of its operands has become ready, right? So then, so the question here is that how do we make a not ready to a ready transition? So somebody needs to let it know. Who lets it know? Well, the solution to the puzzle is that the producer instructions that are producing the value, they need to let it know. For example, let us say that the physical register is P5 and P5's value is being produced and it is being consumed by a later instruction. So at the moment P5 will not be ready, but when the producer produces the value of P5, it needs to somehow let all of the consumers of P5 know. So once the producer finishes executing, it broadcasts the tag. The tag is nothing but the destination physical register ID, as we have seen, to the entries of the instruction window. So if this is the instruction window, all the entries are kind of listening, and once P5 is done, it is sort of broadcast to all of them. All the entries check if P5 is one of their sources. If it is, if the tag matches, if it is one of the sources, they set the corresponding source operand to be ready. So this process is known as wake up. So in this case, we are waking up an operand. It's also known as waking up an instruction. For example, if for an instruction it finds that after a wake up both its operands are ready, then we say that the instruction has woken up. So wake up means that it is ready to execute. What does that mean in this case? Well, what it means is that it can go ahead and read the value of its operands. So this is an important point to make here. The important point that we want to make here is that what is being broadcasted is the tag. So the tag in this case, if there are 128 physical registers, the tag is only 128 log 128 to the base 2, which is 7 bits. So that's all we are broadcasting. We are not broadcasting the value. Okay. So that's a very important point to keep in mind, that we are not broadcasting the value. Why are we not doing that? Well, that will become very clear later on, not now, but it is very important. So keep this in mind. It's an important question, that we are not broadcasting the value. But why are we not broadcasting the value? I'll not tell you the reason now. This kind of food for thought. So I'm drawing a virtual burger. I'm a bad drawer, but this is essentially, like a side view of a burger, right? Add your lettuce and chips and other unhealthy stuff in between. So not broadcasting the value is something we are doing right now. We're just broadcasting a tag, which is 7 bits. 7 bits is not much. A value can be a fat 64-bit value. So that's not being broadcasted. And 7 bits broadcasting is fast and quick. and that this can be done. So what would be a representation of this? Well, the representation is very simple, that in the simple diagram there is a tag bus. So the tag bus is being broadcasted to, so the tag is being broadcasted to both sides. So let's say one side are comparators for the first source operand and the second side are comparators for the second source operand. The tag could match any one of them. So what we have is that for every entry we have two comparators. So for, let's say, this entry, we have two comparators, source 1 and source 2. So for each of them, well, what do? We read the contents of the entry, we read the contents of the tag. If they match, we set the ready bit. Similarly here, if they match, we set the corresponding ready bit. So this is done for every single entry, and for any instruction where both the ready bits are set, the instruction is said to have woken up. So every cycle, whenever we broadcast, right, we will definitely wake up some operands, and we will also wake up some instructions if the rest of the operands are ready. So whatever instructions are woken up, they are said to be in a woken up state. So they subsequently need to be selected, go through the select unit, and then read the values from the register file and execute. So what is this? What is the sequence here? Well, first we dispatch, and once we dispatch, they enter the instruction window. Then of course they wait. Subsequently, the tag gets broadcast by the producer, right? So you broadcast the tag. Then what you do is that you do your process of waking up. You do a wake up. For all the instructions that have fully woken up, we select, right? We select a subset based on structural hazard considerations, and then once we select a subset, we read the operands from the register file. So it could either be the register file or the bypass network. Once that has been done, what do? Once that has been done, well, we don't know much, we just execute. So this process of waking up the instructions, right, and sending them to the execute units is known as issue. So what do? Well, issue basically, if I were to look at it broadly, right, is said where I can basically take the instruction window and from it I send them to the execution units. So this is said to be issuing to the execution unit. So this process is known as issue. So here is a slightly deeper view of it. What we do is we compare both the sources, source tag 1 with the broadcasted tag and source tag 2 with the broadcasted tag, and we set the corresponding ready bits. So this is happening for each entry. Let us now consider the case where we have multiple tag buses. So recall that if we have a multi-issue processor where we send multiple instructions to the execution units every cycle, so multiple producer instructions will become ready every cycle, and they will broadcast their tags. So we actually need multiple tag buses, one for each producer. So this can be producer instruction 1, and this can be producer 2. So the producer instructions can broadcast their tags. So what will actually happen is that we need to compare both the tags that are being broadcasted, tag 1 and tag 2. So let's say for the first source 1, we will actually compare both the tags. So we need two comparators. We need one over here and we need one over here. So both the tags are compared and then an OR gate. So just one of the comparisons will be successful. So we'll never broadcast the same tag. The same tag will not be broadcasted on both the buses. So there will be at most one match. So if there is a match, the OR gate will catch it and it will set the ready bit. Same is the case with the ready bit for the second source, where we will broadcast two tags. And if there is a match, this will be captured by the OR gate and this will set the status of ready 2. So this was the basic broadcast and wake up mechanism. So let us now take a quick look at the instruction select mechanism, which means that once we have chosen the set of instructions, what do we do? So what we do is that let's consider this the instruction window. So in the instruction window, we'll have instructions of two types, red and green. So green instructions are the ready instructions, which are ready to execute, and the red instructions are waiting. So each instruction, there is a wire. So there is a wire essentially for each entry. So we call it the request line. So whenever it is ready, it just asserts its request line, which means sets it to 1. So there are similar request lines connected from the rest of the entries, and all of their status is 0. But again, for the next green line, it is 1. So what the select unit does is that it basically selects one of the requests and grants it. So well, how does it do it, and how does it do it for multiple instruction types and take structural hazards into account? Well, we will take a look at all of those issues, but let us look at a simplistic variant of the problem where we are considering only a single type of instructions, and let's also consider only one functional unit, right? Only one execution unit. Let's proceed with that. We'll gradually complicate the story. So what is the idea over here? The idea over here is that we have n inputs, and so let's say there are a total of n inputs in the select unit. In the n inputs, so out of the n inputs, a few are 1, a few are 0. If it's 1, it clearly means it is interested to be selected. So one among these requests is selected. Which one we will see later. And then the one that is selected, let's say that this instruction is selected, then its grant line is asserted to 1, and the grant lines for all the others remains at 0. So the one that is asserted, essentially that entry can proceed forward and read its data and execute. Alright, so you read the register file subsequently and you execute. So the job of the select unit is pretty much to select one among the n that is interested or whose request line is set to 1. So let us now take a look at a select unit. So a select unit takes in a set of requests, and its job is to assert one of the grant lines, the request that is granted. So the grant lines are not being shown for the ease of readability. So in this case, what we see is we see a tree structured select unit, as you can see over here. These are the different levels of the tree. So the tree need not have a fixed arity. So I am showing a tree where there are 4 leaves at the there are 4 requests coming in at the lowermost layer, and all the internal nodes have 2 each. So it doesn't matter. But what matters is the logic of these rectangles over here. So a rectangle here is called a choice box. So what a choice box does is like this, that it first inspects all the requests that are coming in. They can either be 0 or 1. So let's say if all of them are 0, it will set its output to 0. basically saying that none of its requests are interested. Let's say one of them is a 1 and the rest are 0, well then it's easy. It just remembers the fact that this was the request that it chose and it sets its output to 1. But let us say multiple requests are 1. In that case, it needs to choose one. Well, which one? That we will see. But let's assume for the time being that it chooses one kind of arbitrarily, randomly. Let's say it chooses this one. So then it remembers this choice internally. So internally it has a set of registers to remember which choice. So that's not much. If there are 4 inputs, you just need a 2-bit register. So with that you remember this choice. Then what you do is that the output is set to 1. So this choice box also does something similar. So as you see, so let's assume the output for this is 1. So then this choice box would do something similar. It would remember which input it chose. So let's say it chose this one. It will then set its output to 1. And in this choice box doesn't have a choice. It needs to choose this one. It also sets it to 1. Finally, the root node will make a choice. So let's say it chooses this one. So then it will decide to grant the request. The grant signal will follow the reverse path. It will grant this. Then this choice box will go back to the request that it had remembered, right? So then this is this, and then the grant signal will go via this route. All right. So what we are essentially doing is that we are aggregating the choices in a tree structured fashion. And so this entire thing, by the way, is happening in hardware. So entirely in hardware, right? So whoever thought that trees, linked lists and queues are concepts that are only used in software data structures, that is totally wrong. So you can clearly see an example over here where a tree is implemented in hardware. All right. And right. So this tree over here is entirely implemented in hardware. And so this is of course the VLSI implementation, and all that you require is we need a little bit of state at each choice box to remember which input was chosen. Once that is done, well, we just aggregate the choices, keep going towards the root aggregating the choices, and finally one is chosen and a reverse path is followed. So what we need to do now is we need to create a fairer version of the selection mechanism, but I have a small animation that I can show you. So let us say that we have 2 requests with these blue circles over here. So this is how they flow. They come to the root node. So assume that there are no other requests. The root node chooses one. Then the grant signal, as we have discussed, goes back the reverse way. It requires some state at each choice box. Let us now make the select unit more complicated and more realistic. So what if we have 2 adders, 2 multipliers and 1 divider? Well, a simple solution is that we have a separate select unit for each class of instructions. For example, for the adders, we have a separate select unit. So for this select unit, all non-add instructions are by default not interested, right? Are by default sort of not valid for this select unit. So recall that with an adder, it's kind of an overloaded unit. So it of course does do addition, but it does addition as well as subtraction. And it also computes the addresses of load and store instructions. So in that sense, we typically have more adders than what is required. Then we can have multipliers and dividers. So basically, for multipliers also, we have a separate select unit and a separate one for a divider. So consider a select unit that caters to multiple FUs or multiple functional units, right? So there are separate options for it.
And also, what I mean by this is multiple functional units of the same type. So this basically means that if let's say we have two adders, we'll have one select unit for adders, but again instead of one unit, it will actually have two units, right? Because there are two adders. So in this case, one option, which is a simple one, is we chain select units in the sense we have a set of requests coming in, one of them is granted, and for the line that is granted, if it is one, and we just XOR it with its request, right? So we do it for all, and I'm only showing the circuit for the request that was granted. So for the next select unit, uh, essentially the request for it is 0. That is because it was granted by the earlier one, so it cannot be granted by the second select unit, and it is 0. But for all the other inputs, right? So there are many other inputs, and I'm not showing them. So all of these inputs, are pretty much connected to other XOR units. For each one of those, we'll have a request line, and a grant line which is coming from the previous select unit. So in this case, the grant line for only one of them will be 1, for the rest will be 0. So pretty much the request will show up over here. So the request is 1, it will show up over here. If it's 0, it will show up over here. The job of the second select unit is to basically grant one more request. So that is how, even if we have two adders, by chaining the select units, we can grant two requests. What is the disadvantage of this method? The disadvantage of this method is that the time that is required is double, right? So it requires twice the time, so it is slow. So the signal has to pretty much pass through the first select unit and then pass through the second select unit. So it's roughly 2 times the latency, which is not optimal, right? Which is clearly not what we wanted. So we need to search for a more efficient method. The second method is that we complicate the choice box. So what we do is that we send multiple request signals up to the root. So we have the lowest layer of choice boxes looks the same. So pretty much here we have request lines that are coming in. But each choice box, instead of selecting one request, selects a maximum of 2 requests. So each one of them, instead of one, selects a maximum of 2. So again, they are sent to one more choice box, which again selects a maximum of 2. So on and so forth until you reach the root. So what I say is that we can generalize this. So every level sends at most n requests to the root. The root will ultimately select at most n requests and issue grant signals, where one grant signal might go this way, another might go that way. It doesn't matter. But at the most n requests will be granted. So this, in a certain sense, is faster than the design shown in the previous slide. No doubt it is faster. However, the choice boxes need more elaborate logic, and they become more complicated, right? So it is not, it's a better solution at the cost of complicating the choice box. Let us consider a different design that has asymmetric select units. So in this case, what we do is I have drawn a regular tree structured select unit where there are two copies of the tree and both run side by side in parallel. So let us consider the first select unit, which is select unit 1. So there will be there will be 4 cases. So if you consider this choice box, either both the request lines are 0, well then there is no problem at all. No choice needs to be made. So we can happily erase the ink on the slide. If one of the request lines is 1, then also there is no problem at all, because by default this request is chosen. So we can again erase the ink on the slide, and likewise is the case for the other case, right? If it is 1 and 0, then by default this input is chosen. However, if both the inputs are 1, then the fun lies here. So if both of them are 1 at any level, regardless of the level, the first select unit 1, the choice box gives priority to its left input. What this basically means is that it chooses its left input, right? So the left input is chosen. In the second select unit, each choice box gives priority to its right input, which means that the right input, in this case, this input will be chosen. So it is possible to prove, and in fact I would like to invite you to prove the following, that if I were to design a select unit in this fashion, and if at least greater than equal to 1, sorry, greater than equal to 2 request lines are positive, both the select units will never make the same choice. So this is easy to prove, it's not hard at all. So let's consider the case when only 2 request lines are 1. So of course they will be at different places. So ultimately they will collide in some choice box. Whenever, so wherever they collide, let's say they collide over here, the select unit 1 will choose the left input, while the select unit 2 will choose the right input. So automatically the choices will be different. So this can of course be proved for more than 2 inputs that are set to 1. So it doesn't make a difference. This is a general result and can be proven. So this is a rather fast method of designing parallel select units. So we'll essentially have two, one like this and one more like this. So this gives priority to the left input and this gives priority to the right. And as we see, if we have two adders, then we can make two choices and they will be different. And in terms of latency, the latency is roughly the same and we get twice the throughput. So this is one of the examples of using a smart design method with a little bit of math to actually speed up hardware significantly. I would like to repeat what I said, that it is normally construed that links, queues, trees, etc. are software concepts or computer science concepts. However, that strictly speaking is not true. You are seeing an application of it in hardware. So the select policy has an important implication on performance. So we have till now kind of elided the question on which instruction we should select. So clearly all instructions are not the same. So there might be one instruction and no other instruction is dependent upon it. So that should have a lower priority. But it is possible that there is one instruction, but a lot of instructions are dependent on the output that it produces. So if let's say this instruction is executed and in a certain sense sent forward, right? Then all of the instructions that depend on it, all of them can wake up and the amount of ILP will increase significantly. So the main point of designing a good select unit is to figure out those instructions on which a large number of other instructions are dependent. These instructions should be selected. So of course, how to do it in hardware and that too quickly? Well, that's difficult, but a lot of modern select units actually have some estimate of how to do it. So let's look at this. So one, of course, the most simplest method and yet the most impractical is random, that we just select any input at random. Another option which is fair is oldest first, in the sense we give priority to the requests that are that have been in the instruction window for the maximum amount of time. And given that the instruction window is a queue, from their position we can roughly figure out how old an entry is. But ideally, it should be a combination of the age and the impact. See, any fairness by definition should be a combination of age and impact. So this is kind of a natural rule in the sense that even if a leader is to be chosen, like a village headman or a head woman or a head person, uh, in general, people give preference to age because everybody has a natural respect for age. But along with that, you would also look at the most eligible person, right? The person with the maximum amount of caliber for doing a certain job. So in this case, the caliber is the number of instructions that are dependent on it. But if we always start choosing this, then of course we'll have starvation and that will lead to other problems, which we will see a few slides later. So it should be some combination of basically age and impact. And as I said, it's a general rule in life as well. There are a few other important points to keep in mind. One is that load instructions typically have slightly higher priority than stores. The reason is that if you think about it, who's dependent on a store? Actually, it's a later load, but there are other ways to take care of them. So stores pretty much write to memory, and it is rather unlikely that you would write to memory and you would read it. But we have seen such a pattern in assembly code where you store a register and you read it back. But as I said, we will talk about another hardware structure called a load store queue that precisely captures such patterns. Otherwise, it's kind of rare that we would write to memory and read it back uh, in general code. But in general, for a load instruction, it's on a critical path because the sooner its value comes back, many more instructions will might be dependent on the value that the load brings from memory. So many a time it is seen that load instructions are way more critical, and thus if we have to give a priority, we should give a priority to a load as compared to a store. So most modern select units sort of design a select function, which is a rather complicated function, and also the function can change over time. So a lot of learning is involved over here, which is sort of a function of the age, the impact of the instruction, as we discussed the number of instructions dependent on it, and also the opcode. So the opcode can, for example, loads of higher priority than stores and so on. So based on this, you derive some sort of a score, and this is kind of fed to the choice boxes, and the choice boxes make a choice accordingly. So of course they do become complicated, but well, this complexity is not a bad complexity in the sense that this is a performance enhancing complexity. So there is nothing to be awfully concerned about. Now let's come to another important and rather critical issue, which is how do we broadcast the tag and when do we broadcast the tag? So let us quickly look at this short snippet of assembly code. So these are consecutive instructions with a raw dependency, and so this is writing to R1, reading from R1. So even after renaming, the read after write dependence would remain. So this would of course be in physical registers, but nevertheless there would be a dependence. So what we ideally want is we want back-to-back execution, because after all, in an in-order pipeline with forwarding, they would execute in consecutive cycles, right? So we would have forwarding, pretty much MA to EX forwarding, right? Memory access to execute forwarding, we would have that. But in an in-order pipeline would ensure what is called back-to-back execution or execution in consecutive cycles. If we do not get that in an out-of-order pipeline, then for a long piece of code which has kind of a chain of dependencies, an in-order pipeline would give us a higher IPC as opposed to an out-of-order pipeline, and this is not acceptable to us. So the reason that we went for an out-of-order pipeline is because what we expect is that the IPC of an out-of-order pipeline is greater than the IPC of an in-order pipeline, but programs with a chain of dependencies have a potential of spoiling the party. So they have a certain potential of actually ensuring that the IPC of out of order pipelines is lower, which is something that we should not allow. And what do we need to do? Well, if the producer instruction wakes up in cycle I and proceeds to execution, the consumer instruction should also wake up in cycle I plus 1, which is the cycle just after it, such that there are no stalls in between. Because there are no stalls in between in an in order pipeline, so the same should hold in an out of order pipeline as well. So what does this imply? Well, this implies that we sort of need to design these stages very carefully. So let me look at one design point. So in this design point, let us assume that we are able to optimize our pipeline such that wake up and select happen at the same cycle, right? So if they happen in different cycles, it will introduce more complexities, and it is also there as an exercise at the end of the book. But let's look at the simple case first, and we will then gradually, slowly ramp up the complexity. In cycle I, let's assume we can do both wake up as well as select, right? So that would be like packing two things, two very performance critical things together. But let's assume we have an optimized pipeline and good designers to do it. So then what essentially happens? So what happens is that this part of the pipeline would look like this: rename, dispatch, wake up and select, register read, we read the values from the register file, then we execute, and then we write to the registers. So one of the simple options that we are looking at here is that we actually broadcast over here. And if we broadcast over here, let's see what are the problems. So note that in this pipeline, we have full bypassing and forwarding enabled, right? So forwarding in an out of order pipeline is called bypassing. So in this case, what will happen is that if we broadcast in this stage, uh, we will have to have a 2-cycle delay, as we can see over here, between the producer and the consumer instruction. This delay is clearly not acceptable to us, right? So this flies in the face of pretty much everything that we have been talking about. So what this basically says that, look, in these 2 cycles, we either insert bubbles, which means we don't do anything, or we execute some other instruction. So that possibility is always there. Because it's an out of order pipeline, we can bring some other instructions, instruction X and instruction Y, and they can be executed in this stage, right? So in a certain sense, we can still have a reasonably high instruction throughput, but if you are unfortunate enough to have a code with low ILP, which means that we have a lot of code with these sequential dependencies, right? So the dependencies are like a chain. Clearly, we need to insert a 2-cycle bubble, and there was no need to do it in an in-order pipeline, but in an out-of-order pipeline, we have to do it, which is not something that makes us happy. Let us assume that somehow we are able to, so one thing is that along with writing to the register, we can't broadcast the tag, which incidentally appears to us to be an intuitive solution, intuitive way of doing it, but this is clearly not allowed, right? This is not acceptable. Another approach could be that we broadcast the tag along with execute. If we broadcast the tag along with execute, what will happen is that we can reduce this delay a little bit, right? So we are of course assuming that we broadcast at the beginning of the cycle, and then it immediately catches it, it wakes up and selects, right? That's what you're assuming all happens in the same cycle. So even if this does happen, there is still a 1-cycle bubble. So this is again not acceptable to us. What is possibly acceptable to us. So it's just showing the way that instructions move. But what is possibly acceptable to us is option 3. When instruction 1 is in the register read stage, then in the register read stage itself we broadcast the tag. So this is clearly an early broadcast. So we will discuss the implications of an early broadcast. But if we are able to do it and the instruction 2 catches the broadcast in this cycle itself, right, when we broadcast in the same cycle it catches it, then it can wake up and select. And in this case the execution will be back to back, because then when 1 is executing, 2 is reading the registers, which of course it will not get the right value, but then it will get it from the bypass path, which is in the next cycle, because 1 would have computed its results, so it can bypass the results to instruction 2. So it is important that we see this animation once again, and I'll clear off the ink, and it is important that we see this once again to appreciate what exactly we are trying to say. So what we are trying to say over here is that, look, if you broadcast along with a register write, it's not a good thing. The reason that it is not a good thing is because we will have to introduce the distance between instruction 1 and 2 has to be 2 instructions. Since it's an out of order pipeline, these 2 instructions need not be stalls, they can be other instructions. Nevertheless, we will not have back-to-back execution, which does matter in a code with very low ILP, where we have a chain of dependencies. Even if I were to broadcast 1 cycle earlier, that will still not work because we have this. Hence, what I need to do is that when instruction 1 goes to the register read stage, right, just after getting selected, it kind of speculatively broadcasts the tag. I'm using the word speculative. Well, so in this case, it makes an assumption that the execution will take 1 cycle. So we'll come to that, but so we'll come to the implications of this. But what we are essentially trying to say is that along with the register read, it broadcasts the tag. At the same cycle, instruction 2 wakes up, then both proceed. So naturally, instruction 2 will not get the right value from the register, but that's okay. We can use a forwarding mechanism called bypassing here. So we can bypass the results from instruction 1 to 2, and this will work in exactly the same fashion as the in order pipeline. So what is the option that actually worked? It is early broadcast. This allows back-to-back execution, which means execution of dependent instructions in consecutive cycles. So it does allow this to a certain extent. Well, we will see. So when we discuss later ideas, we will see why to a certain extent. So what needs to be done? Well, when instruction 1 is in the register read stage, 2 needs to be in the select stage. This is possible if you broadcast the tag for 1 when it is in the register read stage. 2 will simply pick up the tag. It is going to wake up and get selected for the next cycle. Alright, so that is all that it's going to do. That it is going to wake up and simply get selected in the next cycle, which is anyway what we want. So the classic example of forwarding in an out of order pipeline would look like this. So by the way, our out of order pipeline now has changed. So I'm not showing the fetch and decode stages. So they are of course there. So I'm showing rename, dispatch, and then wake up select. So wake up select is happening in the same cycle, and then we have register read and broadcast. So we are of course assuming here, it's a kind of a bold assumption, but this needs to be made at least in this simplistic setting, that we broadcast at the beginning of a cycle, and roughly in the same cycle, so not roughly, in the same cycle, the consumer instruction wakes up, and of course if no other instruction is being selected, it gets selected. So the select is again a best case select, right? So it is possible it doesn't get selected in this cycle, in a later cycle, but we are just assuming a tight case. over here. So after this, the consumer proceeds along the same path, and then of course, when it needs the value, there is a forwarding that we can see over here. I should also write bypass. So the word bypassing is more appropriate over here. The value is bypassed and the execution proceeds. So what do we get to see here? Well, what we get to see here is, assume that the duration of execution instead of one cycle is 2 cycles. When can this be the case? Well, this can be the case for a load instruction. In a load instruction, what happens is that we actually spend 2 cycles executing it. Why? The first cycle is address calculation. Right, that is the first cycle, which is address calculation. The second cycle is memory access. All right. So that's the reason what I have done is that I have pretty much created a 2 cycle execute over here. So in this case, of course, back-to-back execution is not possible. It was not possible in order pipeline as well. So there was a 1 cycle delay or a 1 cycle stall. So in this case, the advantage of an out of order pipeline is that we do the same, but instead of actually stalling, we can execute some other instruction in the middle, in this middle cycle, right? We can execute some other instruction. But that said and done, what we do is we don't, in this case, we don't broadcast immediately. That's important. That needs to be kept in mind. We don't broadcast immediately after getting selected, right? So instruction 1 is the load and instruction 2 is the use. So what we do is that we broadcast 1 cycle later, right? Because in this case, it's not a 1 cycle execution. So we broadcast 1 cycle later. And so we, instead of broadcasting the tag here, we broadcast it over here. After this, we have wake up select, we have read and execute. If bypassing is required, then we forward or bypass in this cycle. And as you can see, it happens seamlessly, the same way it would happen in a regular in order pipeline. So what is the key learning from this figure? Well, I'm erasing the ink. I'll maybe give you 5 seconds to meditate on this figure before I tell you the answer. So your meditation time starts now. Okay, 3, 4, 5. So the important point is that for different kinds of instructions, we just broadcast at different times. Right, so what we do is we just broadcast at different times. We don't broadcast at the same time, we broadcast at different times. So for an add instruction, we broadcast in the next cycle, in the register read cycle. And for a load instruction, we broadcast 1 cycle later, which is in the execute, in the first cycle of execute, we do that. So if I were to kind of summarize everything that I said up till this point, so what would it be? Well, what it would be is that we have renamed dispatch, wake up, select, read, broadcast, execute, assuming 1 cycle execute, of course. So for different instructions, we broadcast the tag at different points of time. So we clearly saw that for a regular 1 cycle add and for a load, which by definition takes multiple cycles because of address calculation, we broadcast at different times. So if I were to generalize this, I can say that if the execution requires k cycles, we broadcast the tag k cycles after getting selected. Is this true? Well, all that we need to do is we need to go back. So in this case, the execution requires 1 cycle. So we select in this cycle, one cycle later we broadcast. In this case, the execution requires 2 cycles. So after selection, we wait, after 2 cycles, we broadcast, cycle 1, cycle 2, we broadcast. So this is the general idea of broadcasting. And so if you would recall, I had asked a question several slides earlier. What I had said is, why don't you actually broadcast values? Why do you broadcast tags? So the answer should be clear at this point. Let me just write this down. So why don't you broadcast values? Why do we broadcast tags? Well, the reason we broadcast tags instead of values is because we do an early broadcast, and in an early broadcast, we don't have the value with us, so we cannot broadcast it, right? So we need to broadcast the tag, all right? So this pretty much completes uh, our discussion of the basic mechanism. So we will now look at a more complicated, we'll look at a complicated version of broadcast, slightly more, and we'll look at some corner cases.